I'm going to teach you a little bit more about rotational inertia. I have posted some videos in Edpuzzle for you guys to watch. There may be more. I think the first one is 6 minutes. I think the next one was 14 minutes. Um, so just pointing out, there'll be some videos that I've assigned that will build upon what I talk about today. All right. So when we were talking about rotational inertia previously, what we were doing was referencing physical points, like in the problem, that first problem where we said there was a little ball attached to a rod at these different spots, you might recall. And then there's some torque that's applied and it gets this thing rotating. But we said how rapidly it gains rotational speed depends on how much torque. And again, alpha is the angular acceleration. That's how quickly it gains rotational speed. Depends on how much torque there is, net torque technically, and it depends on the rotational inertia. Remembering that that's similar to, that's similar to this, of course, not over m. And when we addressed I, the rotational inertia, you may recall that we used this formula. And the reason we're able to use this formula is because what we're doing is assuming that all of these objects that were here were objects that have mass, yes, but they exist at just one spot, one point. It wouldn't be the same as, I don't know, if it was something that was shaped like this, and we said, no, the whole thing has mass. All of this has mass. Maybe it's made of wood. You made something like this and you're going to whip it like a frisbee. Then that mass is distributed throughout the whole piece. It's distributed everywhere, right? And figuring out what the moment of inertia would be for that object would be much different in this simplest case over here on the right where we start, where it's more clear that the distance from this axis of rotation out to that point is very clear to draw just from there to there, and it's r. That no one scratches their head on that because it's very easy to say that, again, the distance from the middle out to that point is r. If I said, how about this one? If this was the axis of rotation and this thing was going to spin, like I guess like a fidget spinner, where do I draw r to? Even just for this section, I can start here and draw outward. How far do I go? Any suggestions from either of you? It's not clear, right? Because even if I go all the way to the end, like I did over and put the dot here, you'd say, but that's not where all the mass is. On this other case on the right, yeah, I draw r to there because that's where all the mass is. But in this case, again, the mass is throughout the whole stick. And this is a big distinction between what's called a point mass system or approximation, I'll put. We're approximating these as existing at a point, one point, and single point in space. So when you say point mass in physics, it assumes that all of the stuff is at one particular tiny spot. In the real world, that's not nothing. Nothing has all of its mass in one really tiny spot. I mean, a mosquito does. A mosquito is pretty close to a point mass because it has some mass. I don't know how much it is. It's not the point. The point is whatever amount of mass it has, it's all located in a very small spot. But we get to use this concept of point mass fairly frequently, even though we in the real world have objects look like this, and we don't throw frisbees that look like the one on the right. This, by the way, is considered an extended object. This is what we usually refer to as an extended object with mass distribution, or mass distributed throughout its volume. Volume is just the amount of space it occupies. And when you have, like my body has some volume, some amount of space, and I have weight, body, physical, skin and muscle and bone all distributed throughout, I'd be an extended object. You certainly wouldn't say that all my weight is confined into one spot, one point. But know that those are two different things. And we now started here on the right side, talking because this is the simplest scenario, where we, again, assumed that all of the weight of these balls were in one small spot. And that was a useful formula because we, again, have to add these all, not right, R, M2, R2, R2 squared plus, and you would do that for all of them. But the point is that R is very clear to draw, right? And remember that each object provides some resistance to the rotation. When you grab this thing on the right, my image on the right, and try to give it a zip, each mass that's sitting on the end of these rods provides some resistance. You'll feel it as you try to rotate it. It's not like it just boom, all of a sudden spins. Like you would have to overcome it as you grab that thing, and you would feel a little resistance as you tried to turn it. That total resistance you feel, again, comes from some amount of resistance that each of them creates, and the total has to be the sum of all. So now what we're doing is referencing again today objects like in your lab, which are not point masses. Those were cylinders, and those were rolling down a ramp. And they definitely have mass distributed throughout the whole entire length of the cylinder. Before I talk about that, I'd like to make a couple of comments. Let's look at another similar scenario. Let's assume that there's a beam, and we are eventually going to, relatively soon actually, have to do this kind of problem. Let's say this is a wall, and then there's a beam, and there's some sort of rope that comes down. Now, in this particular problem, there's tension in this rope, and the rope is actually pulling in this direction. This is considered the tension in that rope. It's pulling on the beam in that direction of that dark black vector. And technically, when you're looking at that tension force, it has two components. It has one component here, and it has one component here. And this one would be considered F perpendicular, and R would technically go from here all the way up to there. So we can kind of use this idea that that force that's being applied by the rope is being applied at a particular point, the end of the rope. That's where it's tied. And so again, drawing R is not a head scratcher. You just would say from here all the way out. As long as you recognize that this this right here would be the axis of rotation. If the rope were to cut or break for whatever reason, the end of the beam right here where it's touching the wall would kind of get snagged due to any frictional effect between the left side of the beam and the wall. And the right side would be free to fall. This is assuming that the rope snapped. The right side and the rest of this beam would fall, but the left side, since there would be some pressure right in between there, and that would cause some frictional between the left side of the beam and the wall, that would pretty much stay put. And this thing would first just start to rotate in the clockwise direction. Eventually, of course, after rotating a bit of an angle, the left side of the beam would, of course, separate and start to fall down. But the first moments of that rope cutting, you would end up seeing a rotation of the beam. And the torque, again, that the rope is providing is up because it's due to this F perpendicular. That would actually cause it to rotate this way. So why would the beam in the real world start to rotate down? It turns out it's because it's the weight of the beam itself. It's Earth's gravity pulling down. We call that weight. That's pulling downward on this beam and causing that downward pull. Gravity's torque pulls it in that direction. So if we were trying to understand that a little bit more, which I'm going to try to do now, I'm not sure what my, pull up my larger eraser. Not sure what's going on with that. Just deal with it. So if we were trying to think, all right, if gravity is causing a downward pull on this beam, where do we draw it? We could imagine breaking it into little chunks like this, and then saying, okay, this chunk of the beam out here has some weight pulling down, which is definitely perpendicular to R. This chunk here has some weight pulling down, which is perpendicular R. So all of those points, one moment, please. No. I don't believe so. Yeah, I won't be marking anybody. I thought people were all at a mock exam, so anybody that was out, I wouldn't. I can go back and check because I recorded it. Yeah, if I can call back, because I'm just, yeah, okay. Thank you. Thanks. Bye. Okay. So what I was saying is if you're trying to figure out what the total torque is on this beam by Earth's gravity, again, you might have to think about breaking this into chunks and saying, again, that each chunk has a particular weight, gravity force, and then there's some distance from the pivot point to there, and you call that R. But again, where would you stop? Where would you bring this R to? Would you bring it to the front left side of the block? Would you bring it to the middle of the block? Would you bring it to all the way to the right side of the block? Again, this tackles the question, which is about where the mass is located. That becomes more of a question. So we, again, talk about this concept of center of mass. We certainly have before. Why can I not? There we go. That the center of mass is the most sensible spot. So we put a dot here, and we draw R from there to there. This is considered the center of mass. And because essentially you're averaging out all of the spots inside that little box. There's some parts that are to the right of that center of mass, but there's also some parts that have some weight that are just to the left. Those would cancel out. There's some parts that are underneath that black center of mass dot, but there's also some parts that have some weight that are above it. and they all kind of cancel out, right? And on an average, the average of all those average position is in the center. So my point is that you are, even if you were doing this, you would have to use the point. Now you're bringing the point mass system into place, even for what we're calling an extended object, because the center of mass is the concept of using the point mass idea, so that you can figure out often how much torque something's weight is creating when it has the option of rotating in a downward direction. With that said, you would never do this. You would never do, the torque on this one little piece that I'm coloring in here would be this particular weight times whatever this distance r was. And then, move over to the next piece and say this one has some weight and this has some distance r, and then figure out how much torque that one does, that one creates, and then, add them all up. Nobody would do that. What we would do, again, is just say, well, the whole beam, we can just use the whole beam and say that the center of mass for the beam is in the center of the beam. And instead of taking all the time, if the question again was how much total torque does the beam's weight itself get as gravity pulls in the downward direction on the beam, assuming that it's free to rotate about an axis that is touching the wall, right where it touches the wall. What is the total torque? Again, one approach is break it into segments and add them all up. It could take a long time to do that. Or you just say that the center of mass of the whole beam is in the center, and then the distance from here to the center of mass is here. And then the gravity force, this is the weight of the whole beam. Because the center of mass assumes, the center of mass puts all beams' weight in one spot. So we're assuming that all of the weight of the beam has been collapsed into one single point called the center of mass. And that means technically what we're doing is turning this into a problem where we now have a very thin rod that has no weight. This is like a rod with no weight with a ball on the end. And the ball on the end now has the full weight of the beam. That makes sense. That's what we're doing. What we're doing is trying to force something that's confusing, which is the beam itself, which has weight all over the place, and force the situation which is simpler for us, which is confining it all into one point so that we can clearly draw R from here to here, and then the full weight, Fg, is down with the full weight of the beam. It turns out when you do this method on the right, you get the exact same total torque as you would if you did the method on the left. And the method on the left would take forever to do it, break those into a whole bunch of small pieces. Because each piece to the right is a little further away, a little longer of R. And then the next segment to the right is even a little further R. And you'd have to do that accurately. You'd have to actually make a whole bunch of little tiny pieces and then add them all up. So this is me at least showing how the point mass, that concept of point mass, can still be applied to physical objects that have extended mass and weight that's distributed throughout them. You can still invoke the point mass system, and usually it's to use it for the center of mass, specifically to figure out how much torque gravity, its own weight, is getting as something is allowed to rotate in the downward direction due to gravity. Or that I should say, it doesn't even have to. In the case where this thing is tied to a rope, static equilibrium problem, this right here this still gets torque. Even if there's a rope attached and it's not allowed to rotate down, there's still the same amount of torque in the downward direction. It wants to rotate clockwise, even if it's not, that doesn't mean it's not getting torque. It just means that the net torque is zero, because that rope part that we said before has some perpendicular component to that tension force that happens to be exactly equal in its torque, equal to this amount, so that they cancel and it doesn't rotate. Now beyond that, you've done now a lab where you've seen like cylinders. you did a lab now that had not points rolling down the ramp, but actual cylinders, right? These again would be considered this would be R here. This would be an extended object. It has its mass distributed throughout. And now I wanted to reference moment of inertia because I'm bouncing back and forth between moment of inertia and torque. Originally, the first thing that we did was use the point mass idea of point mass to figure out how we can calculate the moment of inertia for a system that has point masses attached to the end. Then, just moments ago, I explained how you can use the concept of point mass in applications of torque so that you can figure out how far away from the axis of rotation the mass is, and that's the distance from the axis of rotation to the center of mass. And it's still invoking the point mass idea because you're talking center of mass, imagining collapsing all of its weight into one single point. But that was in an application of figuring out what the torque was. Now returning back to a conversation about rotational inertia, about, again, an object that can rotate as it rolls. We know it's going to rotate. And we might say, how do we figure out the rotational inertia for this object? How do we determine it? Can we just say the sum of the masses, like we did before, times r squared? Can we use this? The answer is no. We wouldn't be able to just use outright that because, again, that would be extremely hard. Now what you'd have to do if you wanted to try to do that is actually color in little squares here like this and call that like segment 1, and then another one that, like this, segment 2, and then you'd have to figure out what all of the distances are. God, that would take forever, especially if it's a solid cylinder. It's not just pieces outside the edge that have weight, it's within it as well, right? You could go inside and cut little chunks out with a saw and say there's parts inside that have weight, and they're smaller distances from the center. So breaking that up into a million different pieces and trying to figure out that would be complicated, and that takes calculus. Calculus allows you to do this kinds of sums using what's called an integral. And people in calculus can eventually learn how to apply calculus to this particular problem while doing an integral. And you would actually do something that is an integral, a calculus tool, that's used to add up all of these pieces in terms of their effect or rotation, their total rotational inertia, because an integral in calculus is just a sequence of adding this to this to this to adding them all together to see what the total effect is. So my point is, you would obviously not be expected to do that because many students don't know calculus. Yeah, some do. You just have to recognize that when you do these calculations using calculus, what you're trying to do is derive a formula which is used to calculate the rotational inertia for different objects. They don't expect you to do it by any stretch of the imagination in this course, and they don't even expect you to memorize all the equations. They give them to you in the problem. So let's take a look at what I'm referring to. Here's an example of equations for different shapes. On the far right, you can see the solid cylinder is here at the top left of that image, 1/2 mr squared. If you were using, notice the mr squared is still there. In our formula for rotational inertia for point masses, it was the sum, sigma, of mr squared, right? But you had to do it for all the masses. Notice the mr squared is still there in all of these. The only thing that's different is you have some coefficient, 1/2 or 2/5 or 1/12, and you can look around and see that they all have different coefficients because their masses are not all distributed in the same fashion. For a solid cylinder, its mass is evenly distributed throughout its entire volume. It has some mass, yes, on the edge, like the hoop, but it also has some mass that's much closer to the center. The hoop, on the other hand, has no mass inside the circle. It's all of its weight is stuck out on the edge. And since sticking weight further away from the axis of rotation makes it harder to rotate, because it's mr squared, right? I is mr squared. So I is proportional to r squared. R is representing where is the mass. If you stick all of your weight, like for a tire, out on the edge, which is the rubber tire, that adds extra rotational resistance to it being rotated because I is proportional to r squared. So when r is, you push that mass further away from the center, it's got more resistance. That's why you see this equation for the hoop, I equals mr squared, is more, it's a larger number than the one to the left of it, which is only 1/2 mr squared. That says that the rotational resistance that this object provides, this solid cylinder, it only provides half of the rotational resistance to a given torque as the one next to it, which is the hoop. The hoop, which has all of its weight stuck out on the end, has twice as much resistance, because you can think of that as 2/2 mr squared, and the one to the left of it is 1/2 mr squared. It's only half of the one to the right of it. So again, sticking weight further out always increases the inertia, the rotational inertia. And not only is it about, how far away the weight is, the mass is, it's also a thing about where this axis is. Where's the axis of rotation? Let's look at the far right side of this image, which is the rod. My meter stick can be thought of as a rod, very similar to a rod. And I can rotate it in one of two ways that are common for you to know about in this course. These ones in particular are on the AP exam. But again, you don't have to memorize the formulas. They usually give them to you, but they do expect you to understand how to use them and any concepts related to it. So let's go over one of those concepts. I could technically rotate this rod, meter stick, like this, which is through its center, its central axis. So I'm rotating it around its central axis, as you see, right? There's some resistance to my torque. I'm getting torque actually with my finger in the middle as I push up like that. That's providing some torque. But there is some resistance to me rotating it. Surely if I were to tape, something like a heavyweight piece of metal on the end and add some weight to this, I'm adding some m in the mr squared. If I stuck some, duct tape and tape this piece of heavy chunk of metal here and heavy chunk of metal here, and I tried to flip that around, of course, would be extremely hard and probably impossible because my fingers can't possibly provide enough torque to overcome how much rotational inertia it would have if there was, in fact, these metal weights attached to the end. That said, there is still some rotational inertia. It's much less without the weights. There is some rotational inertia to me trying to rotate it, to my torque that I'm providing. But that rotational inertia is not the same amount of rotational inertia as I would experience as if I held it on the end. And now the axis of rotation is where my fingers are. Here, the axis of rotation is where my fingers are as well. It's an axis of rotation in the center. If I go on the end, now the axis of rotation is at the end. And if I'm trying to swing it like this now, in loops around like this is actually much more difficult for me to swing. When I actually do that, I can feel that there's my fingers have to push with more force to get this thing to zip around, much more than when I go like this. I can just barely flick it. In fact, look at the acceleration. I mean, this thing goes from staying still to rotating very rapidly, pretty quick. Where on the end, it's much more slower in gaining speed. It's indicating that there's more rotational inertia when I hold it like this than when I hold it like this. It's not because it's a different stick, it's the same stick. It's not because there's different weights, it's the same stick, it has the same weights. It has, again, to do with how the weight is distributed in distance from the axis of rotation. So if you pick the axis of rotation right in the middle, you have mass distributed on both sides, and no one piece of wood is further than 50 centimeters from the central spot, because it's a meter stick. The furthest chunk of wood is 50 centimeters away on both sides. However, when I go like this, the furthest chunk of wood all the way over here is now a full 100 centimeters away from the axis of rotation. That means it's providing more, that little chunk on the end is providing far more rotational inertia than the pieces that are closer to the center. Because again, pieces that are further away provide more rotational inertia. And that's why when you look at those, the bottom right is referencing that there's more rotational inertia. It's the bottom right, rod about end. That's the one where I'm winging it around its end point. 1/3 is and L, by the way, is just the length of the stick. L is not the distance from the axis of rotation to the end. L is just what is the length of the stick. You're spinning it on its central axis. For this meter stick, L would be 1 meter. If I'm spinning it on the end like I am here, what number would I stick in for L? 1 meter. L is always the physical length of the stick, regardless of where you're holding it. You'll see that the coefficient, on the other hand, is much larger for this one that I knew was more difficult. 1/3 is a much larger fraction than 1/12. How many times larger? 4 times. Because you can think of the 1/3 as 4/12, right? 1/3 is like 4/12. Comparing 4/12 to 1/12, 4/12 is 4 times larger. So that means I experience 4 times as much resistance as I try to rotate this around an axis that's on its end point as I do compared to when I try to rotate it around its middle point. With all of that said, these different objects are ones that are commonly referenced on AP exams and that you have to become familiar with. The solid cylinder is on the left. Even if the physical solid cylinder is shortened, so like this can of spray is like a solid cylinder, even if the length of this came all the way down to only being from here to here, like a hockey puck, it's still called a solid cylinder. The length of the cylinder, and I guess if you're holding it this way, you'd call it the height. But if it's sideways, you usually call it the length of the cylinder. The length doesn't matter. Doesn't matter if it goes from here all the way to here, or if it's just from like where my fingers are, which is like a hockey puck width. Those are still solid cylinders. And notice that the physical length is not even in the formula. There's no L on there. M1/2 mr squared. R is actually the distance from the center out to the end. This is R. No measurement sideways is in this because the physical length of that cylinder doesn't matter. I haven't explained why yet, but I think you discovered that in the lab. Describe that another day. But for now, it suffices for you guys to know that you have to be aware that different objects have different resistances to being rotated. Usually they reference nice geometrical objects. Symmetrical, they have symmetrical distributions of their, so they're nice, just geometrical objects. But not all things are geometrical. I mean, think of, I'm looking around my room. Like, is this a symmetrical object? Definitely not, right? Like, can I just spin this around its center like so nicely, like this one, because this is geometrical and symmetric on both sides? No, right? They're not, but this is a weird shaped object, right? There's different extra weight on one side, less on the other. And so they don't have you deal with those. We'll talk about them later. They're just referencing nice geometrical objects. You have to know that they all rotate with different resistances, assuming that you're applying the same torque to all of them. They all won't rotate and gain speed at the same rate. The ones that have the greater rotational inertias will gain speed more slowly, and the ones that have less rotational inertia will gain speed more quickly, assuming you're applying the same torque to all of them. And also, you need to know, again, that the axis of rotation can change. And as soon as you change the axis of rotation, like in the rod, for example, that turns up on the AP exam a lot, that rotational inertia changes. And therefore, it wouldn't speed up as rapidly if the end point is the axis of rotation versus the middle. So know that those are things we're going to reference more. Oh, did I go over? I think I went over by 7 minutes. I'm sorry. I'll reference that some more when I see you guys next. Let me flick back to see if I can still see you there. Yeah. So just keep an eye on Google Classroom. Again, I posted a couple short Edpuzzle videos. I think I'm also going to record something of myself doing, some extra lesson as well. So just keep an eye out there. Then there's the other reminder that the practice exam, those questions would be, I think the first set of questions 1 through 15 were due tonight. And then the last set, 15 through 30, were due yesterday since that was classwork. You also had the lab, the rotation lab with the hoops or the cylinders. Hopefully had enough time to do that yesterday. I think you should have. And that grade's closed today. That's all I have to say. Any questions from either of you, I should say? All right. Have a wonderful weekend. I'll see you next week. See you later. Bye bye.